Lesson is not a super long lesson. It should be, you should have 15, 20 minutes at the end of the lesson to be able to work on some assignments and get some things done. Like I said, I know some people already worked ahead and already have some of it done. Hopefully, if you were one of those people, and hopefully it made sense to you. If not, hopefully after the lesson today, it'll make more sense of what you were working on. Quick warm up here. 3 to the x equals 27. What's the answer? 3. Okay. So some of these problems you can just do in your head. The problem is, and here's what we're going to talk about today. Well, what if you can't? What if it was 3 to the x equals 25? Not a nice number. No giving up and going home. What if it's base e and therefore not a nice number? Okay, e to the x equals 3. What if that's the problem? And therefore, here's our objective for today. Solving exponential and logarithmic equations. Okay, how do I solve these equations? The good news is the process for either of them is fairly the same. Pretty much the same method that you're using. Okay? But that's what we're going to take a look at as we work today. So here's your process. Let's start with exponential equations. Okay? You've kind of got 2 things to take a look at. Option number 1, if you can do it, this is what you should do. You should make the same bases, okay? If you can get the bases to be the same in your equation, you should do it. Because once the bases are the same, then you can just set the exponents equal to each other and solve from there. So this is going to take knowing that you have the same bases. And I'll go back to the warm-up for a second so you kind of know what I'm talking about. But the reason I start with this is this allows you to not have to use a calculator. Okay? You don't need a calculator if you can do this. So here's what I mean in general. Let me go back real quickly, and then I'll come back to this. So like on the 3 to the x equals 27, let's say it just didn't make sense off the top of your head, which I'm not worried about it. But 3 and 27 are both powers of 3. Therefore, I could rewrite this as 3 to the x equals 3 to the third. Okay, 27 is just 3 to the third power. And therefore, x equals 3. If you can get the bases the same, then you'll set the exponents. Now, you wouldn't need to do that in that scenario. I'll give you an example in a second where it would come into play. But that's the idea what I was talking about. If you have something like this, the 3 to the x equals 25, well, 25 and 3 are not both powers of the same thing. So that doesn't work in that scenario. Which leads us to the other option. If that doesn't work, then here's your process. Okay? Step number 1. You isolate the exponential part. The 2 to the x, the 5 to the x, the e to the x, whatever it is. You isolate that portion of the equation. Some problems it'll already be isolated. You won't have to do anything. Okay? Other problems you'll have to get it by itself, and I'll show you both. Okay? That's step number 1. Once you have it isolated, you then are going to switch forms. You're going to use the definition of a log to change it to logarithmic form. Okay? And you'll see why. It makes the problem easier. We always use logs to solve exponential equations. And we use exponents to solve logarithmic equations when we get there. Okay? But the idea is isolate number 1, then switch forms number 2. Once you switch forms, then you can solve. So those, anytime you see an exponential equation, those are kind of your 2 options. If you can make them the same basis, go ahead and do it and then solve from there. You don't even need a calculator. If you can't, then you're going to have to go through and isolate and work your way through it. Okay? So let me show you a couple of examples where you see a little bit of everything. Okay? So example number 1. 8 to the x equals 4. So first question, are 8 and 4 both powers of the same base? What is it, Carson? Yeah, we can change those into both powers of 2. So 8 is really 2 cubed. So I'm going to rewrite this then as 2 to the 3x. Okay. X is still up there. And 4 is 2 squared, which means now, since the bases are the same, the exponents have to be. So now I don't have to worry about the bases anymore. They're already the same. I can just focus on the exponents, which means 3x has to equal 2 in order for these two to be equal to each other. And now we solve for x. Divide both sides by 3, and you find out that x equals 2/3. Okay. Notice no calculator needed for this one. Okay. You could use a calculator and solve this, which I'll show you in a second. But this is when we talk about the calculator versus no calculator day. This could be a problem on the no calculator day, because I don't need a calculator to do it, because I can get the bases the same. Okay? If we double checked, by the way, just as a quick, going back to Algebra 2 for a second, if you remember fractional exponents, the top number of the fraction is the power, the bottom number is the root. So 8 to the 2/3, if I think about it, and let's say I rewrote that as a radical, that's really the cubed root of 8 squared. Okay. What's the cubed root of 8? 2. And 2 squared gives you 4. Okay? So that's just giving you a heads up, just refreshing your memory a little bit about fractional exponents. Remember, the bottom number of the fraction is always the root that you're taking, and the top number is always the power that you're then raising it to. Okay? So just a quick check, just so you can see it and understand that it makes sense. Okay? So there's option number 1. If you can get the bases the same, do it. Option number 2. If you can't get the bases the same, then we'll do method number 2 here. So 4 to the x equals 15. 4 and 15 are not powers of the same base. So in this scenario, we go to the other option, okay? Which I had said isolate the exponential part. Well, the 4 to the x is already by itself, so we're already past step number 1. There's nothing left to isolate, which means let's change this into logarithmic form. Okay? If you remember earlier in the chapter, we went back and forth between exponential and logarithmic. Here's where it's coming into play. So we always start with the base. So therefore, this is going to be log base 4. Remember, the logarithm always equals the exponent. It's giving you the answer for the exponent, so we're going to set it equal to x, which means the 15 is the argument. Okay. Start with the base. They have same bases. A logarithm is always equal to the exponent. So whatever's in the exponent, that's what you're always setting it equal to. And then whatever's left, in this case it's 15, that is your argument. Okay. Now if you take a look, is x by itself already? Yep, don't even have to solve for anything. Type it into the calculator. Log base 4 of 15. Okay? So again, if you have the log base on the calculator, you can type it in directly. Okay? You want to go back over it? Let me go back over it. Let me switch to the calculator. So if you're typing that in directly, there we go. You would go to the math button on the calculator, right below the alpha button. Arrow up, and then you should have log base as A. If you hit that, you can then fill in the base and the argument, whatever it is. Okay, so in this case it's 4, and then the other one was 15. You hit enter, and there's our answer, approximately 1.95. Reminder, if you have a TI-83 calculator that does not have the log base on it, you have to use the change of base formula, which says take the log of the argument. So if you actually hit the log button of 15, make sure you close the parenthesis, and divide it by the log of the base, in this case 4. You hit enter, and notice you get the exact same thing. Okay? So if you can enter it directly, you're more than welcome to do so. If you can't, then you got to use your change of base formula. Log of the argument divided by the log of the base. That's how you have to enter it in otherwise. Okay? Quick heads up then. So the answer is approximately 1.95. Let me go back to the problem here for a second. So we get x equal to approximately 1.95. Quick question. Why does that answer make sense according to this problem? because 4 squared would be 16. So the x being a little bit less than 2 makes some sense. Okay, so it's a reasonable answer. Okay, so option number 1, get the bases the same and just work your way through it. Option number 2, if not, you can always go to logarithmic form. Okay? Let me give you another example here. So in this one, same starting point. We would always isolate the exponential part, but again, the base is already by itself. This is only 2 to some power. There's nothing multiplied, there's nothing added or subtracted at the end. The base is already by itself, which means we're going to go to logarithmic form. We're going to use our definition of logs. So we have log base what? 2. Yep, log base 2. What are we going to set this equal to? The exponent. No matter what's in the power, it's always equal to the exponent. That's what logs are giving you. So x plus 1, which means the 7 is the argument. There's flipping it from exponential form into logarithmic. And now, once again, it becomes a whole lot easier. Log base 2 of 7, you can type into the calculator. What do you get, by the way? 2.8? Somewhere in there? Okay. So 2.8 equals x plus 1. And now subtract the 1, and you've got your answer. Therefore, x is approximately equal to 1.8. How are we doing? Making some sense, hopefully? Okay, let's make it a little bit more complicated, but not too much. We just haven't had to isolate anything yet. Okay, everything's already been isolated. So, last exponential example. For e to the 2x plus 2 equal to 15. So now, those other 2 examples, we didn't have to isolate. There was nothing, it was already by itself. This one, we need to get the base with the exponent by itself. I need to get that e to the 2x by itself before we switch forms from exponential to logarithmic. Okay? Which means I need to get rid of the 4, and I need to get rid of the plus 2. So as we do that, it's just like solving any other equation. Subtract the 2 to the other side. So we've got 4 times e to the 2x equal to 13. Divide both sides by 4. Get that 4 out of there. So now we're at e to the 2x equal to, I'm just going to leave it as 13/4. You could divide it. It's, as long as you don't have to round, it's okay to use the decimal. If you would have to go through and round that decimal, then leave it as a fraction. Okay? Don't round until the final answer. Now I've isolated the exponential part, which means now I can switch forms. Okay? Since this is base e, what kind of log am I going to deal with? Natural log. So we're going to go the natural log, okay, which is already base e, equal to what? Equal to the 2x, which means the 13/4 is your argument. Always equals the exponent. And now, once again, we're pretty much ready for the calculator at this point to finish this off. What is the natural log of 13/4? 1.19. Okay. So approximately 1.19 equal to 2x. 1/8, did I heard? 1/8? No, okay. That's good. That makes it easier to do in my head anyway. Makes the math easier. 1.18 equal to 2x, and now you just divide both sides by 2. We end up with approximately 0.59 as our answer for x. So realistically, when you solve exponential equations, some of them you'll be able to get the same bases. Most of them you won't, and you'll have to isolate, change forms, and solve. Okay, that's kind of the basic idea when you work your way through this. Quick question, by the way, before we go to logarithmic ones. When we were graphing exponential functions, what do we say the domain is all the time? All real numbers, right? The reason I bring that up is that means x can equal anything. Positives, negatives, 0, doesn't really matter. I don't really have to worry about what x equals. It equals whatever you end up with. But what do we say about logarithmic? You can't take the log of a negative number, which means we have a restricted domain, so x can't equal anything. Something we got to consider when we go into logarithmic equations. Okay, so let's switch to that. Like I said, the good part is the process is pretty much the same. Instead of having a base, you have a logarithm. Okay, instead of an exponential base that you're solving for. So step number 1, isolate. But this time, instead of isolating the exponential part, you're isolating the log or the natural log or whatever it is, okay, whichever type of problem you're working on. But you're still isolating. I put condense in here because when you're solving logarithmic equations, this is why we did that the other day. It's so that sometimes when you condense it down, it makes the problem easier to solve. Okay? So there may be some condensing you have to do, and I'll show you an example where we have that. But step number 1 is isolate. Step number 2, same as before, switch forms. Use the definition. Switch it from logarithmic form into exponential form, because it makes it easier. And then solve. Isolate the log, switch forms, and solve then the resulting exponential form. Just like we were doing before, it got easier after we switched forms. Same thing will happen here. Once you switch it into exponential form, it's going to get a lot easier to solve. There is, however, one extra step, and we talked about it just a little bit here ago. And that is, you do have to check for extraneous solutions. Because of the fact that you can't take the log of a negative number, right? Anytime there's a restricted domain, it's possible that you're going to end up with an answer that x can't equal. So you got to make sure you check. I didn't have to worry about it with exponential because the domain was all real numbers. X could equal anything. Logarithmic, not so much. X can't equal anything. Let me give you an example to start with, a straightforward example to start with. All right, so if you take a look at this one, you've done this, by the way, already, just as a heads up. Remember when we were graphing logarithmic logarithmic equations, you had to find the x-intercept? So we said, let's set the log equal to 0 and solve. It's the same thing, except it's just not equal to 0. It happens to be equal to 3 in this one. Okay, but you've already actually solved a problem like this before. So if we go through and we take a look, step number 1, we said isolate. Well, the log is already by itself. You've got the log base 5, in this case, of something. There's nothing outside of the log. So in this case, we're then going to go, let's switch from logarithmic form into exponential form, starting the exact same spot every time with your base. 5, what's the power? Yeah, remember we just said before, logs always equal the exponent. So the exponent is the 3, and therefore it equals x plus 2. There's exponential form, just work in the opposite direction now. I said this gets a lot easier because now we can pretty quickly solve for x. What's 5 cubed? 125 is equal to x plus 2, and therefore x equals 123. If we double check just real quickly, I said you should always check for extraneous solutions. If I plug 123 back in, the argument then is 125. Is the log base 5 of 125, does it equal 3? Yeah, 5 to the third power does give you 125. Okay, so we've got a correct answer. There's no extraneous solution here on this one. Okay. All right, let me give you one more example. We'll simplify this a little bit more to this one. And then, like I said, I'm going to give you some time in class to work and ask some questions as you're working through some problems. All right, so this one's a lot messier. It's not just the log equal to something, okay? It's a natural log problem, and there happens to be 3 of these natural logs. Which side of the equation do you think we should start on? Okay, why left? Because I've got 2 logs that I'm adding together, which means I can condense them into one. I can make this problem simpler. So if I condense these 2 logs, since I'm adding, what do I do with the arguments? Multiply. So this will become the natural log of, if I take x times x plus 3, we get x squared plus 3x. And now let me relate this back to something else. Let me go all the way back to the first problem here. We said on example number 1, if you can get the same bases, that means the exponents have to be equal. Well, in this case, if you've got 2 logs that are already equal, then the arguments have to be equal. Okay? Just like the idea where we got the bases and we set the exponents. Here, we've got 2 equal logs. Therefore, we need 2 equal arguments. So x squared plus 3x has to then equal x plus 8. And now we're right back to an Algebra 1, Algebra 2 type of problem. How do I solve that? Get it equal, yeah, just a quadratic. So solving quadratics, you always get them equal to 0. So if I subtract the x over, we get 2x. If I subtract the 8 over, now it equals 0. Now what do I do? Factor or quadratic formula. This one is factorable, so I'm going to factor it. And we get x plus 4 and x minus 2 as our 2 factors. 0 product property then to finish this off. We get x equals negative 4 as one possible answer, and x equals 2 as the other possible answer. Why do I say possible answer? We got to check to see if it actually works or they're extraneous. Let's take the negative 4 and plug it back in. Extraneous or does it work? Right away you know it's extraneous. Why? Natural log of negative 4. Can't take the natural log of negative 4. Okay? So I know that negative 4 is extraneous. If I plug 2 back in, I just have to check to see if it forms a true statement. So I would have, I'll just do it off to the side here, we would have the natural log of 2. If I plug it back into the next one, plus the natural log of 5 equal to the natural log of 10. And that's really a question. Does natural log of 2 plus natural log of 5 equal natural log of 10? Yes. Yeah, think about your properties again. When you add the logs, you multiply the arguments. Sure enough, that one works. Okay? So biggest thing I want you to understand for today, when solving these equations, isolate, change forms, solve. Okay? That's the main idea for today. That's your process of when you're working with these types of equations. That's kind of how you work your way through it. Okay? Unless this one you happen to have 2 equal logs. The first one we did was the exponential one where you could change the bases. Okay, that was possible. And those are kind of some extra scenarios. Here's the assignment. Okay. 221, 17 to 37 odd, 45 to 53 odd. Okay, kind of work your way through it. I will give you a heads up. The first, I want to say 4 questions are ones where you can get the same base, and therefore you should try to do it without a calculator. Okay, I want to say it goes through 23 off the top of my head. I think 17 through 23 are ones you should be able to do or hopefully can do without a calculator. Okay? And you got the rest of the time, the last 15 minutes here, like I said, 15, 20 minutes to work, and I'll answer questions if you have them. Let's go to work.